Okay, hi. In this lesson, we will learn about the system of linear equation. We know that the general form is ax plus by equals to c, where a, b, and c are real numbers. If it has more variables involved, then the equation will become like this, where this is the linear equation in the end, with variable of x1, x2 until xn, or the coefficient, and the b here is the constant term. So a finite collection of linear equations in the variable of x1, x2 until xn are called the system of linear equation. Example, we have x equals to 2, y equals to 5, and z equals to 0. And x equals to 0, y equals to 4, z equals to -1. These are both solutions to the system of x plus y plus z equals to 3 and to x plus y plus 3z equals to 1. For instance, if we substitute our x and y into x plus y equals to 2 and x plus y equals to 3, then it will be wrong and we have no solution because the sum of two numbers cannot be 2 and 3. Therefore, if the system has no solution, it's called inconsistent, and a consistent of system called if there's at least has one solution. Example show that for arbitrary values of s and t, where x1 equals to t minus s plus 1 and x2 equals to t plus s plus 2, x3 equals to s, and x4 equals to t. It's a solution of the system of x1 minus 2x2 plus 3x3 plus x4 equals to -3, and 2x1 minus x2 plus 3x3 minus x4 equals to 0. The solution is just substitute the x1, x2, x3, and x4 in each equation. So the first equation will become like this, and the second one will become like this. The s and t called parameters, and the set of solutions by parametric called the general solution. Another example, describe 3x minus y plus 2x equals to 6 in parametric form. So if we want to get y from this equation, we will get like this. Am I right? And if s and t are the arbitrary, then the x now equals to s and z equals to t. So our solution becomes x equals to s, y equals to 3s plus 2t minus 6, where the s and t are the arbitrary and the z equals to t. We can also solve x by x equals to 1 over 3 times y minus 2z plus 6. If we assume that y equals to p and z equals to q, then the solutions are x equals to 1 over 3 times p minus 2q plus 6, y equals to p, and z equals to q. Actually, this has the same solution as before, but look quite different. If we plot in the Cartesian, it will look like this. So suppose the first equation is x minus y equals to 1 and the other line is for x plus y. We have the intersection in P2.1, and this is called unit solution of x equals to 2 and y equals to 1. And if the line graph shown like this, then it has no solution because there's no intersection in between lines. And if this result like this, then it has infinitely many solutions. Okay, suppose we have these three linear system equation. It's quite difficult to solve by elimination and substitution at the same time. So to obtain it, we can transform that into matrix like this, and this is called augmented matrix of system. Here is our coefficient matrix, and this one is constant matrix. For example, we have x plus 2y equals 2 minus 2 and 2x plus y equals to 7. So our augmented matrix is like this, and to solve, we subtract the 2x plus y equals to 7, 2x plus y equals to minus 2 twice, and we got the result like this, and the augmented matrix like this. The y here equals to minus 11 over 3. And here we also subtract y equals to minus 11 over 3, 2x plus 2y equals to minus 2 twice, and got x equals to 16 over 3, and y is minus 11 over 3. So the augmented matrix is like this, and our operation way is called elementary operation. Now we move to the elementary row operations. So this operation need to change the augmented matrix like this. This for two variables, and here is the coefficient, and this is the constant value. And for three variable will be like this. Example, suppose we have 3x plus 4y plus z equals to 1, 2x plus 3y equals to 0, and 4x plus 3y minus z equals to minus 2. Then the augmented matrix will become like this. Okay, and to solve it, we need to change this coefficient number into this form. So first, according to our form, these 3 need to be changed into 1, right? We can just multiply this by 1 over 3. But if we did that, what about this? The result will be not satisfied with our form, right? So we can change this value by subtracting it to the row 2 and got the result like this. Now we need to change this into 0. We also subtract these all row values into row 1 twice, and then we got like this. Okay, next, this guy also need to be changed into 0. So we subtract this into row 1 4 times and got the result like this. Okay, next we need to clean this into 0 too. Then just subtract this row to this row and add this row to that row. So our result now like this. The result has no effect to the first row. Then we multiply this minus 7 with minus 1 over 7, and our result will become like this. And then we subtract this first row with row 3 times, and we add row 2 to row 3 twice. And then our augmented matrix now like this, and this is row for x, y, and z. Then our solution are x equals to minus 3 over 7, y is 2 over 7, and z is 8 over 7. It has 3 types of the evaluation. Type 1 is by interchanging two rows is reversed by interchanging them again. Type 2 is multiplying a row by a non-zero number k is reversed by multiplying by 1 over k, which we just did before. And type 3 is adding k times row p to a different row q is reversed by adding minus k times row p to row q. Note that p is not equals to q is essential here, so the step can be seen in example here. Okay, let's move on to the Gaussian elimination. We know that this augmented form is a nice matrix to solve our system, right? Now we will reduce the row by row echelon form, where the step is first, all the 0 row are 0 at the bottom. Second, first non-zero entry from the left in each 0 row is a 1. It's called leading one for that row. The third, each leading one is to right all of leading one s in the row above it. The fourth, each leading one is the only non-zero entry in its column. So our matrix will look like staircase. Example, here we have 6 coefficients and we need to reduce each coefficient value into 0 and put one in between coefficient and constant value to look like staircase. Example, we have the equation of 3x plus y minus 4z equals to minus 1, x plus 10z equals to 5, and 4x plus y plus 6z equals to 1. Then we transform them into augmented matrix, become like this. First we move the second row to here, then our matrix become like this. Then we just subtract the second row to the first row 3 times and the third row to the first row 4th time. Then our matrix will look like this. From this matrix, the coefficient value at the last row still not 0. Then we just subtract the second row to the last row and got the matrix like this. So our reduced equation becomes x plus z equals to 5, y minus 34, z equals to minus 16, and 0 equals to 3. This two has solution, but this one has no solution. So the equation has no solution. Another example, we have the equation like this. Then we transform into matrix and we reduce it using the echelon form and got the result like this. So our reduced equation become like this, and if we set x2 equals to s and x4 equals to t, then the arbitrary s and t equations become like this. And our final looks by substitute the x2 and x4 will become like this. The last but not least, we move to the homogeneous system. Example, suppose we have an A matrix with a coefficient as seen on the screen. Then we want to reduce the augmented matrix and look like this. So the solution of x1 equals to 2s plus 1 over 5t, x2 equals to s, x3 equals to 3 over 4t, and x4 equals to t by Gaussian elimination. So for x, we can rewrite the equation become matrix like this, and the system can be rewrite as sx1 plus tx2. So this form will be used when we are studying the state space transformation in the control system later. So I think that's all for this lesson. Thank you for watching and see you to the next lesson.